Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome to the NPTEL online certification course on environmental degradation of materials and surface engineering. So we are into module 7, lecture 33, and this is about a very particular technique called shot peening. So, as the name suggests, this is about shooting very small spherical objects, hard steel balls, at times ceramic balls, onto the surface of a component with an objective of creating residual compressive stress primarily, and also make that stress appear uniform throughout the surface. Now, before we begin, take a look at this very large roll, and each one of them would be weighing several tons and made out of alloy steels, very expensive. A single roll could cost about 1 crore or even more, and they have a certain service life. Now, let's say either due to manufacturing practice or fault or defects created during the manufacturing of the roll itself, or during the processing, that means rolling of various feedstocks, either the temperature was too low or the feed was actually given in a non-uniform manner so that the stress got concentrated over a period of time. But most importantly, if the surface over a period of time either developed or already had right from the beginning residual tensile stress, at least in pockets, then it could lead to such very major and catastrophic failure, where a portion of the surface, like as you are seeing here in this red box, is completely spalled off. It broke out of the main surface and rendering the entire roll completely unusable anymore. And this is basically the main reason for this kind of a failure is fatigue crack growth. And as you can see here, just below the cracked region, which actually separated from the surface, just below that separated chunk, you see very textbook-like striations growing gradually from one end where the crack initiated into the surface. And this is typically called the ribbon fatigue, which happens almost like radially propagating striation lines moving towards the other end of the surface. And eventually, when the plasticity of the material cannot withstand this stresses developing inside anymore, then the whole chunk leads to completely brittle or sudden failure. So we would like to certainly arrest this, and this is very important, not just in a roll, but look at this failed crankshaft. You know very well that these kind of crankshafts are very useful for transmitting dynamic motion or load from one end to the other. And as you can see, the various parts of the shaft, 1, 2, 3, 4, they actually, not all of them underwent the failure or developed such a crack. But here you can easily see at point number 4, there is already a crack which has been detected by certain dye penetration or non-destructive evaluation process. And this, if it is continued to use, then certainly this part will crack and will separate. In fact, these kind of cracks typically happen when you see such marks or deformation marks developing onto the surface, which eventually gets concentrated at particular regions. And if the stress concentration becomes too large and crosses the fracture limit, then micro cracks develop, then they combine, and when the micro cracks combine, then that leads to a larger crack opening, and which can lead to a catastrophic failure. So similar cracks you are seeing here on the top surface. So all these examples, and this is a different kind of a crack. This happens because of thermal fatigue. So this is a break disk, and at each time, and this is a curved surface, please remember, and these cracks are completely perpendicular or normal to the curvature. So these cracks develop when material tend to flow more than its elastic and plastic limit, and eventually that amount of deformation cannot be supported anymore, and the total amount of energy input is higher than the fracture toughness of the material, then such cracks develop. But this is not yet catastrophic because these are hairline cracks which have developed, but eventually unless they are arrested and repaired, then it might lead to a complete catastrophic failure. So when we see such cracks, then we realize that on moving parts or dynamic parts of engineering components, particularly which are in deep rotational at high RPM, that kind of a service, or they undergo complex variation of stress cycle in association with temperature or any other activation, then the surface requires certain amount of special attention in terms of preparation before they actually are put in use. So how do you take care of them? And this is where processes, surface engineering processes like shot peening comes very handy. So it's basically a cold working process. You're not changing composition. You're not subjecting to any high temperature or any thermal activation. Purely by cold working, that means you're deforming a very controlled layer from the surface up to a limited thickness, introducing dislocation, certain amount of dislocation density, and creating plastic strain with a purpose to actually confine the deformation within a small region, so that eventually the material that gets deformed would like to regain, and in the process should develop a residual compressive stress. So imagine we have a surface here like this, and here is a projectile, a spherical object coming at great velocity and hitting the surface. Immediately at the point of contact, there will be certain deformation zone, and material would like to flow out of this dent or indentation, and that can happen up to a certain depth, and below that material will try to push back. And during this pushback operation, there will be a residual compressive stress created, because the stresses initially while deforming, the stresses were acting away from the surface, and now when the impact is over, the region below the surface, which now tries to regain, would like to actually come back and fill up the gap, and in the process there will be a stress gradient created which is directed towards each other and onto the surface. So that's creation of amounts to creation of residual compressive stress. This is for a single shot. If this shot happens multiple times by a number of shots or spherical objects hitting the surface in tandem, covering the entire surface area, then you create a entire surface region up to a certain depth of residual compressive stress. So that's shot peening is all about. But these spherical objects that we are talking about actually is not as big as this. They are actually pretty small, 0.5 millimeter, 0.6 millimeter, or even less. And they're made up, as I said, made out of steel, high alloy steel. Obviously, then the density is higher. At times, they could also be of alumina or zirconia, such spherical ceramic oxides, which have very high elastic modulus, apart from, of course, being able to deliver the right kind of impact energy. So what we need is a gun which will throw these shots at great velocity, and these shots are of similar within a very close tolerance limit, variation limit of diameter, 0.5, 0.6 or even less diameter, and they hit, these are basically turbine blades and fins which are subjected to such compressive stress development practice, so that the blades develop residual compressive stress and can withstand very high level of fatigue, even thermal fatigue. Now, as I said, why do we do shot peening? We do basically to create residual compressive stress. Now, if you think of a mechanical property, then these properties actually can be very effective up to a very limited depth from the surface. If we are talking about residual compressive stress or surface hardening effect, please remember there is no thermal component here. Otherwise, the plastic strain that we develop will be dissipated through crystallization or certain other kind of stress relief operation. So this is done entirely at room temperature, or maybe even if there is a adiabatic temperature rise, it won't be more than a few degrees or few tenths of a degrees. So the properties are confined only within the very narrow surface region, which is the so-called short pinning region. Below that, we have a transition region where the stress will actually change from being negative or compressive into gradually going into the deeper inside the material where it could be tensile. So in effect, in practice, one can actually detect a neutral plane where the residual stress will be zero and then becomes tensile. Now, this is true not only for applicable not only for materials which are like a roll or a cutter or something, it is also applicable to materials or components which are exposed to fairly high temperature. So, short pinning, basically there are three important components that we have to worry about. What is the media that we are using, what is the intensity or velocity with which it is heating, and that will be the that will determine the momentum transfer, and the area coverage, whether we are doing in very specific location or over the entire surface, and most importantly, are we able to cover even on the intended surface region. Let's say this is the surface region we intend to cover. Are we doing in localized inhomogeneous manner or doing uniformly throughout the surface? So these are very important things, and because unless it is uniform, then within that short pinned region, a crack may generate and propagate. So this is the mechanism that we need to pay attention to. That, let's say this is a fairly magnified view, a large object, let's say this particular sphere with certain momentum, mass and velocity hits the surface, creates a dent. That's what we expect, okay? Now, obviously, the velocity, the weight, the mass of the material, the velocity, the incidence angle, everything matters, and that will determine the amount of incident energy that is transferred onto the material. The surface also has to be able to withstand that energy. It should not be something like a silicate glass. I mean, it's not applicable to silicate glass or very high modulus and hardness oxide ceramics and so on, because they have practically zero ductility. On the other hand, if you take metal like steel, aluminum, or any metal for that matter, and incidentally, this is one important point I must mention, that short pinning is applicable irrespective of whether it is steel or aluminum alloy or any metallic material, for that matter, any solid which actually can undergo certain level of plastic deformation is amenable to such short pinning operation. So that's why it's fairly universal. And we are neither changing composition nor changing any major dimension. Only the surface region is getting deformed and in a controlled manner, so that we are able to develop the desired level of stresses. So for a single event, if we magnify, we can imagine that this is the deformation region, and as we deform, there will be a tendency for the deformed metal to flow out and form these ridges. But this doesn't happen unless the diameter of the ball is very large, very high. But in this particular case, as the material tries to deform, it tries to push the grains away from this point of contact. And there's a limit up to which the material can flow laterally away from the point of contact. And when it can no longer push the grains beyond, then from that neutral plane, after the impact is over, the region around will try to push the material back into its original form. And that's typically the nature that we expect for material having both elastic plastic deformation characteristics. So due to the elastic nature of the deformation at that point, all the grains in the neighboring region will try to push the material back into the deformed region. And as a result, we develop stresses with directions as shown by these arrows, which are directed towards each other. Now, what is the advantage? If I have a crack like this crack can open and propagate further, provided the state of stress, at least at the crack tip, is acting away from each other. That means tensile in nature. On the other hand, by doing such short pinning, if I can create uniform state of stress up to the limited depth or desired depth, where the stresses are acting towards each other, just opposite to this, then in order the crack to propagate, we first have to convert the residual stress on the surface from compressive to tensile, acting away from each other, and then only this crack can propagate. So, in the event of either having a possibility of such crack formation, or in worst case, a crack exists, a crack already exists even before we have done this operation. In either case, creation of such state of stress which is acting towards each other will actually diminish the possibility of this crack opening further or leading to any amount of failure. So, that's the main technological advantage and objective for which residual compressive stress is created by short pinning. Now, how do you do that? So, this is the surface. So, these are indentation marks. So, here is a single impact which is happening, and because of which the shot is after hitting this point is reflected back. And depending on the angle, as I said, angle and velocity and the diameter, elastic modulus, all these material and process parameters, the amount of impact that we develop here and the corresponding deformation level and its character is created. Now, this is a single impact, but if I have multiple such impacts, each one of them will create certain dimples or dents. Now, if these dents are throughout the surface and uniform, then obviously we can create a surface which will have uniform deformation throughout up to limited depth, and there will be minute, hardly about, since I told you that about the diameter of the sphere that's hitting is hardly 0.5 millimeter. So, you may expect not even 0.1 or 0.2 millimeter depth of deformation region. Now, this mechanical process or short pinning process is pretty similar to laser pinning operation, but we'll cover the laser pinning operation in the next lecture. But it's very important to say that given a choice and precision is important, then obviously one will resort to laser pinning. For the simple reason, if you read the last line, it says mechanical pinning methods can only produce 35% of these depths. So, this depths of useful stress zone creation. So, that means laser pinning will be lot more effective than mechanical short pinning. In fact, it is also known that when we resort to such pinning operations, instead of a single pinning operation, that means using the shots of same diameter and in the same spraying operation, if it is actually repeated with another operation with smaller diameter pins or smaller diameter spherical objects or balls, then actually the effect is even better. So, another possibility, another variant of short pinning could be a possibility where the material is stretched, for example, either by subjecting to some rolling operation or tensile stretching operation. If the material is already stretched, then the grains already have reached the limit of their elastic deformation. And now, if you hit with an object, immediately you'll go into the plastic zone. So, with a lesser amount of energy input, one can produce equivalent or even deeper level of pinning or deformation, subsurface deformation. And in the process, one actually can end up making deeper or higher magnitude residual stress, compressive stress on the surface. So, dual pinning is when you repeat the same short pinning operation with slightly smaller diameter pins or smaller diameter spherical objects, so that, and with lower intensity, so that you simply do add on. It is, you already have created residual compressive stress up to a certain region, and now let's say the depth is about 0.2 millimeter, but on the top 0.1 or 0.05 millimeter, you can create even deeper residual compressive stress, larger residual compressive stress by repeating with the dual peening operation, the second peening operation. As an alternative, one can even try, and this is also very effective, a strain peening operation where the material, say a flat piece or a curved piece, already has been stretched up to the elastic limit. And now if you subject it to short peening, then the degree of peening operation and the impact will be a lot better. What is very important here is to look at this curve. So what we are seeing is that this is the stress magnitude, this is the neutral level. On top we have tensile component. So the material in blue is in tension and the material in yellow is in compression. And from the surface, actually the depth, the peak of the residual compressive stress is not necessarily at the very surface itself, because you can easily make out that this kind of a deformation zone or the so-called dent creates the maximum accumulation of strain or dislocation density, not at the surface, but below the surface. So the peak residual compressive stress is at a subsurface region. In this case, it's at 0.25 millimeter region, and then it changes. It gradually moves towards positive value, 0, and then becomes positive. So until about this kind of a depth, which is, let's say, typically 0.75 millimeter, the state of stress is still compressive. So the material is safe against fatigue or any such deformation or cyclic operation, which may lead to formation of a crack and propagation of crack because of cyclic motion or cyclic nature of the stress application. Please remember that the cyclic nature of stress application, or typically what leads to fatigue, is not necessary that it has to go from tension to compression through the neutral plane. Even in the tension region or in the compression region, if the stress is applied in cycles of very large magnitude to very small magnitude, even this kind of a stress gradient during the operation, cyclic operation, can lead to fatigue failure or fatigue crack creation and propagation. And against all these, this is a very good insurance to prevent any such crack formation during fatigue operations. So, as I said, there are many advantages. It's a fairly simple and inexpensive and can be used for all kinds of metals, not just steel. But obviously, because you're throwing small objects, so full surface area coverage is difficult, particularly when you have very sharp corners or difficult geometry. And the shots themselves have to be replaced regularly. Why? Because they themselves get deformed. I mean, they are not hard ceramic objects. They are also metals themselves. So they also undergo a certain level of deformation, initially only elastic and then eventually also plastic. And when plastic deformation occurs, then the object is no longer 100% spherical, and at the deformed region, the impact is no longer point. The impact can be flattened, and or the surface may be flattened. As a result, the impact area is no longer tangential, but slightly broader, and that reduces the stress intensity that you can transfer. As I already said, that complex shape and geometry is an impediment to utilizing short peening operation. So I've just listed a number of applications where short peening is routinely used: gears, cams and camshafts, clutch springs, connecting rods, gear wheels, leaf and suspension springs. This is a very important operation because the springs continuously undergo such buckling forces, bending forces, because of which both the surfaces undergo alternate cycles of tension and compression, and these are very typical cases where fatigue failure is very common. Then rock drills or turbine blades or any rotating or cyclically components which are subjected to cyclic stress operations, stress cycles are quite common for developing such failures. So if you just look at the hardness as a pointer, then what you realize that at the surface, obviously you have the highest hardness because the strain hardening is maximum at the surface, and it decreases as we go deeper inside. Now, if you have two kinds of materials using stainless steel shots of smaller diameter and stainless steel shots of the same material with a larger diameter, then you realize that the ones with larger diameter, they create a greater amount of hardness, and it actually goes to deeper depth. The reason is very simple, because with bigger diameter, the mass is higher, and hence the impact energy or the energy that you are able to transfer at the point of impact is higher. So the degree of straining is higher, and hence not only the hardness higher, but it actually penetrates to deeper region. Now, on the other hand, but let me also mention that this is about the depth, but when you are using smaller diameter, then the penetration is shallower. So the hardness retained on the surface is higher. Okay. Similarly, when you are doing similar operations with multiple prior deformation or prior history, let's say this particular curve is when the material was not peened and had a notch, and so the failure under fatigue will be much faster and at a much lower, will show very lower fatigue strength. On the other hand, so this is basically the normal curve or the typical deformation behavior or strength behavior expected, this broken line. And as you can see, the material which is peened, which has been subject to short peening, and hence the surface is smooth or notched, in either case, this will show a greater fatigue strength. So having short peening obviously is much more beneficial than the cases when the material is not peened and notched. When in such case it will fail much earlier, and not peened with yet the smooth surface can show slightly higher strength, but the maximum amount of fatigue strength you can see when the material is not only subjected to short peening but also is smooth. So this is the kind of cycles to failure needed for various loading conditions, and the materials are which are in use are nitrided or gas carburized pins, and as you can see that as you do gas carburizing, this is the level of number of cycles or at a particular given load that one can withstand, and this is for gas carburized condition followed by short peening, and this is only gas carburized. So obviously this dual processing, please remember gas carburizing produces martensite, which also produces residual compressive stress on the surface. So on top of that, if you also do short peening, you get the highest dynamic load bearing capacity. And purely nitrided may also produce residual compressive stress, can show a certain fatigue life, but the life obviously is improved when it is not only nitrided but is also followed by short peening. And as you can see, the number of cycles required for failure is much higher. So we have seen that how it also can vary. So if you do steel with lower hardness, with higher hardness, this is the level of compressive stress, depth of level up to which you can create compressive stress. This is steel with higher hardness, and this is aluminum. This is steel with lower hardness. This is titanium and steel with slightly higher hardness. So as the degree of hardness increases, we see the depth of compressive layer that is formed is shallower. So obviously, it will not fetch the same level of fatigue strength or fatigue improvement in fatigue property as we can see with softer materials like aluminum or soft steel or titanium alloys and so on. So we end just with certain riders to you that we need to address what is short peening, what is the operation we are talking about, and why do we do short peening on the surfaces, what we try to develop on the surface, and which way is that useful. And one important thing is that all the while we have been saying short peening And what is peening, by the by? So if you look at this hammer, you have one flat surface, which is one obviously you'll use to maybe insert a nail on the wall or on your wooden furniture or somewhere. But the other surface is curved. And this curved nature of the surface is called peen. So when you say shot pinning, you actually are using a spherical object and making use of this curvature of the surface to create loading on the impacting surface, which is point in nature or tangential in nature. So that's where the name comes from, shot pinning. So shots are those spherical objects, and peening is the operation by which you're taking advantage of this curved surface so that the stress concentration is at the point contact or tangential contact. Then these are the other points that one should look into: how compressive residual stress is created on the surface, what is the role of dislocation, where is it maximum at the surface or slightly below surface, and why we need such a stress condition on the surface to arrest what kind of failure, and what are the typical process parameters of shot pinning, and what is the level or extent of improvement in properties that we can expect. Okay, so thank you very much.